So we've been talking about logarithms and their properties. There's one more property I wanted to mention, and it might sort of play into a bit of a fear you might have at this stage looking at this stuff. We've talked about the base 10 common logarithm, the base e natural logarithm. We've seen examples where a few other bases are floating around, and it may feel a little intense that there's so many possibilities available. You know, why does my calculator only have those two log keys? Is there some sort of general command hiding somewhere that'll let me do a base 3 log if I need it or something along those lines? Your calculator may have one of those, but it turns out you don't really need it. When it's all said and done, we really only need one logarithm. And as it turns out, the key to why that works is something that you might call a change of base formula for dealing with logarithms. So suppose you're wanting to work out a base b logarithm for some number. So I've got, say that's like a base 5 or something, or a base 2 or something like that, of some other, of some number x. It turns out if you know how to calculate stuff using a different logarithm base, we don't actually need to work out what's going on in this base b situation. As it turns out, we can work out the base a log of the number that we're interested in, the x, and that's not an underline, that's actually a division bar, because what we're going to have underneath it is the base a log of whatever this other logarithm base is. So it turns out we really only need one. If you're comfortable with the base 10 common log, you could do just log x over log b. If you're a math, guy like me, and you prefer the natural logarithm, that works out just fine. You could do ln of x over ln of b, and again, it'll work out just fine. So, for example, suppose that for some reason or another, we need a base 2 logarithm of 15. So, again, your calculator may have a base 2 log hovering around in there somewhere, or a fill in the blank for your base type log command. We don't need it. So I'm going to use the natural log instead. So I'd have the natural log of 15 divided by the natural log of 2. So if I put that into my calculator, I got approximately 3.907 if you go to 3 decimal places. So that can be pretty handy. As it turns out, I did want to show you, what if I use the base 10 log instead? You're going to get the same thing. As confirmation, I have my calculator display right here, and maybe a little fuzzy, but hopefully you can tell I did the base 10 log, I did the natural log, I got that same 3.907 either way. So that's that done. So as it turns out, there's one more example I want to take a look at where the change of base property can end up giving us a way to get at something. So we're actually going to need to use some other stuff that we've talked about in this section along the way as well. So kind of, educators like to call that synthesis. So the final thing I want to take a look at is referring to an example toward the very back of the notes file that you've obviously kept handy while we're looking at this stuff, referring to how to calculate how long it takes for an investment to double. So we give you this guy right here. So we have 1 plus whatever our interest rate is, divided by 100n, where n is however often we're rolling interest into the account as the year goes along. Then we have, in the exponent, we have n times t. So the example as we're presented with it gives us an annual interest rate of 8%, and we're compounding interest quarterly. That's 4 times a year. So we can feed r equals 8. Don't convert the percentage into a decimal. I did that one time, and it really threw everything off. So we're going to leave the r just as the integer 8. That's what that division by 100 is doing, in case you're curious. Feed in n for 4. So that gives me 2 equals, when I work out what's in here, I have 1 plus 8 over 100 times 4. It's going to be 400. And I'm just going to leave 4t up top. So if I clean that stuff up in there, I'm going to have 1 0.02 to the 4t. And t is what we're after, the time frame it's going to take our investment to double in whatever, double from whatever we started with. So now I'm going to come back. This looks like the thing we started with at the very beginning, right? Let's see. We have x equals a to the y. X equals a to the y. I can convert that into a logarithmic expression using the somewhat weird feeling base of 1.02. Again, bear with me. So now I can reinterpret this as, let's see, I'll have 4t, because I have y equals the base a log, so I have the log base 1.02, again, it's okay, of 2. So y equals log base a of x. So we've got x, a, y. Okay? Now, my calculator doesn't have a log to the log base 1.02 key. Crap! Oh, wait! That change of base thing that we just did. So, again, I'm going to use the natural log. You could use base 10 if you like. It's fine. And I can work out what this number ends up giving me. I'm not going to quite yet, though, because I don't really have t by itself here. I'm going to go ahead and divide both sides by 4, and then, So we have ln of 2 up top, 4 times the ln of 1.02 in the bottom. Again, if you had worked this out and gotten a number and then divided by 4, you'll end up in the same place. By the time that's all said and done, I get a doubling time of a little more than 8.75 years. So hopefully, that's what you were wanting out of your investment, because unless you get a better interest rate or more compounding or something, that's what you're stuck with. So that's the change of base formula and how we can use it in action. Even with this, though, you may end up feeling this is a little bit unwieldy, having to keep poking back at this, base definition to come up with, what we need, and then having to jump through the, change of base formula. As it turns out, there are some handy properties that we're going to be able to use in order to tackle these things a bit more directly. By the time it's all said and done, we'll have a more direct approach to this guy rather than sort of leaning through that change of base approach. But before we get there, I need to go back and revisit some properties of logarithms that we jumped over in our last video. You may recall I started with property 3, and that seemed a little weird, like I was having a forgetful moment. I wasn't. So those first 2 properties you might refer to as inverse properties of the logarithm. That's one way you might describe them. It's if you don't, that's okay. There was a blank earlier that talked about logarithms and exponentials being what we would call inverse functions of each other if you wanted to fill in that blank. We don't really need to get into the technicalities of what that means so much as we can use logarithms and exponentials kind of to undo each other. So if we have an exponential floating around, we can use a logarithm to get rid of it, and vice versa. So the idea here is that if we have our typical log/exponential base, and we start with an exponential expression, if we apply the corresponding logarithm of base a log to this thing, we're going to get back x. It's not 100% appropriate to mark through these. That ends up feeling kind of strange. I'm not a big fan of that, but you can think of it in some senses, the operations are canceling each other. By the same token, if we started with a logarithm, we can toss that guy into an exponent. The verb I would use for this is exponentiate, but don't worry about that. It can get awkward trying to describe what this ends up meaning. But if we apply a logarithm and then apply an exponential after that, same thing ends up working out. They sort of remove each other from what we're doing, escort each other out of the dance hall, if you will, and we're just left with x in each case. So these inverse properties, as it turns out, are going to be what we use to drive solving equations where exponents show up in our next section of material. So that's where we're headed. Stay tuned and you'll find out more next time.